All right, we are back for just a quick video wrap up of our last two, or the end of the last section and our next section. The next section is really, really quick. Um, so in the last video, we took a look at vectors in two forms. We looked at that component form where it kind of looks like an ordered pair, and it's talking about if this is a position vector and it's starting at 0, 0, the point that it would end up at is 7, negative 2. And we could also look at it in unit vector form. I apologize in advance. My cat just jumped up right next to me, so you might hear her in this video. We'll see. Um, so I and j are those little unit vectors, 1, 0, and j is 0, 1. So we have those two ways that we can talk about vectors, and they basically are kind of giving us the same information. So another way that we can look at vectors and talk about where something is positioned is illustrated in this next example here. So we've got a plane is traveling at 500 miles per hour west to east at a heading of 300 degrees north of east. So remember that we talked about in the last video that you can set up your axis as your x-axis is east to west, east and west, and then your y-axis as north and south. So if we're headed uh, west to east, so we're starting here at the origin, we're going to go out this way. We're going to go out east, but we're being told that we're at a heading of 30 degrees north of east. So this is really telling us our direction. And so we're going this way. And this angle that we're making with east here is 30 degrees. Let's get my handwriting a little bit better there. So 30 degrees. And then our magnitude is actually going to be this speed here. So we are going 500 miles per hour, and that is going to be our magnitude. So if we call this like P, I don't know, I'm just giving it a name for plane maybe, its magnitude is going to be that speed, it's going to be 500. So one of the ways that we could talk about where this is ending up here and the direction that we're headed is we can look at this as a right triangle, and this point here is xy. That's exactly what we were doing up here when we were looking at that component form. We're talking about it ends at xy. Well, think about another way that you looked at this in trigonometry was that we said that sine of that angle, that 30 degrees, is our opposite side over our adjacent side. And that's not opposite. Opposite is y, right? This length, which is our opposite side, is y. This length here, which is our adjacent side, is x. So that sets us up for cosine. I do like to do parentheses around those. So cosine is our adjacent side over our hypotenuse. So we can think about this as if we multiply both sides by 500 in both of these equations, we get 500 times the sine of 30 is that y component, and 500 times the cosine of 30 degrees is our x component. So our vector, we can say, is 500 cosine of 30 degrees and 500 sine of 30 degrees. Now we absolutely could, determine what the cosine of 30 degrees is. It's square root of 3 over 2, and what the sine of 30 degrees is, and it's 1/2. So we could also write this as 250 square root of 3 and 250 if we like it sort of in that format. So that also gives us a way to take it back to component form, but we can absolutely leave it in this sort of, kind of strange looking form right here in terms of sine and cosine. But it's totally okay. That's another way that we can leave it, and it's a way of showing what that direction is in terms of an angle and that speed of that plane. So the thing that we didn't talk about, we didn't get it all to 13.2 in the last video, and that is really all of the same things we learned in 3.1, but in 3 dimensions now. That's really the big difference. And what's nice about it is there's not really any difference when you move to 3 dimensions from 2 dimensions in terms of how you add vectors, how you subtract vectors, how you do scalar multiplication, or anything like that. So we just have to think about, okay, just how does this look in terms of our world when we go into 3 dimensions from being in 2 dimensions. So we're going to look at what's called the 3D coordinate system, or we can also call it the XYZ coordinate system. And so the XYZ coordinate system, so you've got your XY coordinate axis here sort of laying flat. So it's the XY plane. It's laying flat here. And then we go up and with the Z axis, because we add that 3D component. So I'm going to erase this here. Don't worry, it's not really going to erase my axis. There we go. So when we talk about like plotting points in 3D, it is going to be an X, Y, Z coordinate triple. It's not a coordinate pair anymore. So say we had 3, 2, 5. So this is telling us to go, 3 units on the x-axis, 2 units on the y-axis, and then 5 units on the x-axis. So how I kind of view this is that I've got to go out the 3 and go out the 2. So go out 3, then I go out 2, and then I have to go up 5. So it'd be sitting kind of out here. And again, we have to sort of use our imagination because we're kind of drawing a 3-dimensional thing on a 2-dimensional thing. So sometimes what we can do is draw in this as a box, because sometimes that's really helpful to see where this point actually is supposed to be. And I clearly did not do a good job of drawing that point. We will learn this about Sarah this term. I am really bad at drawing pictures, so let's maybe adjust where this purple one is, because this actually does help me draw this much better. It should kind of sit right there. There we go. Much better. So another way to kind of think about this 3-dimensional system is you can kind of think about the origin being a corner of a room, and that the floor is the XY plane. And then like the left wall here, that's called the XZ plane. And the right wall here is our YZ plane. We always do these in alphabetical order. And I don't like all that on there, so we're going to erase it. There we go. And we're going to be able to have vectors in 3 dimensions, and we'll still have those little unit vectors just like we did before, but now they will have 3 components. So I is still sitting on the x-axis, and it goes out 1 unit and then 0 to the y-axis and 0 up on the z-axis. J, it goes 0 on the x-axis, 1 on the y-axis, and 0 on the z-axis. And then we add k. So again, notice alphabetical order. Goes 0 on x, 0 on y, and goes up 1 for the z-axis. So if we wanted to, say, do a vector here, it's going to be hard to draw from the origin that goes up to our point here. If we wanted to draw that red vector, which maybe we'll call that v, would be 3, 2, 5, or 3i plus 2j plus 5k. I'm always bad at remembering to put my little arrows up above. Make sure I wanted to say everything I wanted to say on that picture. I think I did. Okay, so just a couple of other quick notes about the 3D coordinate system. So we talked about, that XY plane, which really is our 2-dimensional graphing plane. And I didn't talk too much about that. So the way that we look at this, so X coming straight out in the front, these are our positive values. Oh, got a little crazy there. These are our positive X values, and here's our negative X values. Same with over here on the Y axis. These are positive. Going sort of back is negative. Up is positive on the Z axis, and down is negative. Okay, we don't need that on there anymore. The other thing that I wanted to mention is that we might take a look at some really simple um, three-dimensional functions in this section here. And one of them is just planes. So a plane is like a line, but in 3 dimensions. And so it's kind of like a piece of paper. So if we say here y is 3, and oh boy, again, we get to see how badly Sarah draws. If I wanted to draw the plane where y is always 3, look something like that, and we could say that y is equal to 3. So it is a vertical plane, and no matter what x or y or x or z is, y is always going to be 3. So all of the points, all of the order triples that sit on this plane that we made here, any place that I pick, the y value is always going to be 3. So that's sort of a simple plane. Of course, we could have ones that are um, x equals, and that would be going the other way here. That would be going this way. Again, not good at drawing things. And if we had a z equals plane, it would look flat. So I kind of view these as these are pieces of paper, sort of infinitely big. And we'll talk about what it looks like when we take that plane and we just tilt it a little bit so it has a slope to it, and it's not like vertical. Let's see. Just trying to think if there's anything else I wanted to do on this slide. Oh, I think I did want to do an example. So, yep, good thing my lovely program here is nice and has extra pages on the end because I forgot. So let's just take a couple three-dimensional vectors and just do a couple of operations. So you've got an example with those. So again, like I said, you know, if you're doing just a simple vector operation like a minus 3b, it's exactly what you think, that it's going to be vector a minus 3 times vector b. So we're going to get 4, 0, 3, doing nothing to that one, and then minus negative 6, 3, and 15, and then we just subtract the components. So 4 minus negative 6, 0 minus 3, and 3 minus 15, and we get 10, negative 3, and negative 12. And again, if we wanted to write that as those multiples of those unit vectors, it would look like that. We can still find the magnitude of a vector, and it's nice when it's a position vector because it's just each of the components squared, like that. And so we get 4 plus 1 plus 25, which is going to be the square root of 30. So again, that's the length, that's the distance, you know, that you're going from 0, 0 out to that point, negative 2, 1, 5. That's that length of that vector. If we had our vector defined as 2 points, we would do it just like we do in 3 dimensions, but we'd have a third component on there. So that's really the biggest difference when you're in 3 dimensions. When you're doing just sort of these simple operations with vectors, it's, oh, now I've got a third component. I have to deal with the x component. And that's it for this one.